Your brain insists the universe makes sense, but it was never built to grasp infinity, quantum strangeness, or even most of the light passing through this room. Evolution shaped your mind for short-term survival on a savanna, not for decoding cosmic reality. That's why so much of the universe feels wrong, from impossible scales to rules that defy story and meaning. But what if the fault lies not in the cosmos, but in the very structure of your mind? The real shock comes when you see exactly how deep these blind spots go. 1 million years ago, the most important thing a brain could do was spot danger before it struck. Every neural pathway, every flicker of attention was tuned to the snap of a twig, the glint of water, the subtle change in a companion's face. The machinery inside your skull was shaped by the need to dodge predators, find shelter, and read the intentions of others, never to chart the birth of galaxies or trace the arc of time. Evolution built a brain that excels at quick judgments and snap reactions, not at holding the scale of light years or the logic of quantum uncertainty. In fact, most of what your brain calls reality is a best guess, assembled from scraps of sensory data and filled in by habit and expectation. As neuroscientist David Eagleman put it, "What is reality? It's whatever your brain tells you it is." The world your mind builds is a simulation, one that's good enough for chasing antelope or avoiding snakes, but not for grasping the universe's deepest rules. The visual system, for example, focuses on a tiny area of detail and blurs the rest, trusting memory and prediction to fill in the gaps. Our sense of time is wired for the next meal, the coming storm, not for billions of years or the split-second chaos of the early universe. Even the way you judge distance is rigged for the 10-meter dash, not the span between stars. Experiments show just how narrow this window is. Infants can track objects only on human scales. Adults misjudge the steepness of hills when tired because the brain warps perception to save energy. The tools we use to survive, pattern recognition, agency detection, spatial reasoning, are all tuned for the familiar, the nearby, the now. When faced with infinity, randomness, or the absence of a center, these same tools falter. The universe isn't broken. The brain just wasn't built for this. Visible light is just a sliver of what actually exists. The electromagnetic spectrum stretches from radio waves the size of buildings to gamma rays shorter than atoms, but the human eye can detect only a tiny band, about 0.0035% of the full range. Everything beyond this, from infrared warmth to X-rays from distant galaxies, passes through us unnoticed. Even the most familiar senses barely scratch the surface. Sound is limited to a narrow window of vibrations. Touch cannot register the atomic forces that hold matter together. The world as we know it is filtered by the blunt tools of biology, tuned for survival, not for truth. Numbers tell the story. Every second, more than 1 million neutrinos pass through a square centimeter of your body. These ghostly particles, born in the hearts of stars and the violence of supernovae, slip through Earth as if it were empty space. Their presence is as real as sunlight, yet no nerve or sense organ ever registers them. Instruments like the IsoCube Neutrino Observatory in Antarctica are needed to catch even the faintest trace, buried deep under ice, waiting for a rare collision to spark a flash of blue light. The universe is not silent either. Radio waves from distant quasars, microwaves left over from the Big Bang, and gamma-ray bursts from collapsing stars fill the cosmos with signals. Without telescopes, antennae, and detectors, this symphony remains forever hidden. What feels solid and complete is mostly absence. Our senses are locked in a prison of evolutionary design, giving us only a keyhole view onto a reality that is vaster, stranger, and more complex than the mind can grasp. Scale itself becomes the enemy of intuition, and the numbers reveal just how much lies beyond the reach of human perception. Brains are built to find meaning, even where none exists. When lightning flashes or a shadow moves, the mind leaps to causes, a hidden animal, a lurking enemy, a sign from the gods. This urge to see patterns and assign purpose runs deep. Psychologists call it apophenia, the tendency to spot connections in random data. In one study, 73% of people attributed agency to moving shapes on a screen, seeing intention in what was only chance. The same wiring that once saved lives on the savanna now insists that the universe must have a story, a reason, a central character. But the cosmos offers none of that. Galaxies drift apart not because of a plan, but because space itself stretches. Stars explode and new worlds form, all without meaning or direction. Agency detection, another survival tool, primes the mind to expect someone or something behind every event. This bias helped early humans avoid danger. Better to mistake the wind for a predator than the other way around. Today, it makes the universe's randomness feel like an error. When a meteor wipes out the dinosaurs or a supernova seeds the elements of life, the brain aches for an explanation beyond physics. Yet the evidence points to indifference, not intention. Pattern seeking and agency detection are double-edged swords. They make sense of chaos on human scales, but falter at cosmic ones. The universe unfolds according to laws that care nothing for narrative. There's no cosmic script, no built-in meaning, just processes so vast and impersonal that the mind recoils. The feeling that something is off, that reality should make more sense, comes not from the universe, but from the machinery inside the skull. Meaning is a story the brain adds after the fact, a comfort in a world that offers none. Galaxies appear to rush away from us, but the truth is stranger than motion. In the early 20th century, Edwin Hubble measured the light from distant galaxies and found it stretched, shifted toward the red end of the spectrum. This wasn't a sign that galaxies were speeding through space like cars on a highway. Instead, space itself was expanding, carrying everything along with it. The farther a galaxy lies from us, the faster it seems to recede, a relationship captured by the Hubble constant, about 73 kilometers per second per megaparsec of distance, according to the latest local measurements. That's not a speed limit for objects, but a feature of the universe's fabric. To picture this, imagine dots drawn on the surface of a balloon. As the balloon inflates, every dot moves away from every other, not because the dots are traveling, but because the surface between them is stretching. No matter which dot you stand on, the view is the same. Everything recedes, and no single point holds the title of center. This metric expansion breaks the most basic intuition about motion. In everyday life, movement means something traveling through a medium, a bird flying through air, a boat gliding across water. But in cosmology, the medium itself grows. Physicist Sean Carroll describes the math behind this as a shift from thinking in terms of objects and speeds to thinking about distances changing without objects going anywhere. The redshift law, confirmed by decades of observation, proves that the universe's expansion isn't about galaxies racing away, but about space itself stretching everywhere at once. The numbers leave no room for intuition. What looks like motion is really the dynamic growth of the cosmos itself. Stand anywhere in the universe, and the view looks much the same in every direction. There's no sign pointing to a cosmic center, no edge where the stars run out and darkness takes over. The universe, on its largest scales, is both homogeneous and isotropic, meaning it has no privileged spot, no up or down, no special vantage point. This idea runs so deeply against the grain of human experience that it can feel almost vertiginous. On Earth, every journey has a beginning and an end, every map a center and a border. But the cosmos offers no such orientation. The Big Bang did not explode from a single location into empty space. Instead, space itself has been expanding everywhere at once. Every galaxy, no matter how distant, finds itself at the center of its own observable universe, watching others recede into the distance. Evidence for this radical symmetry comes from the afterglow of the Big Bang, the cosmic microwave background, or CMB. This faint radiation bathes the sky with a temperature uniform to within about 1 part in 100,000, or delta T over T approximately 10 to the minus 5. Across 13.8 billion light-years, the difference between the hottest and coldest spots is less than 1/1000%. No matter where the measurement is made, the result is nearly identical. The few tiny ripples that do exist seeded the formation of galaxies, but the overall smoothness is staggering. It means that, at the grandest scale, the universe refuses to give us a reference point. For a brain tuned to find its place, to search for boundaries, landmarks and centers, this featureless expanse is deeply disorienting. The mind wants an anchor, a wall, a signpost. Instead, the universe offers endless repetition, a structure so uniform that every observer is equally unimportant. The loss of orientation is more than philosophical. It's a direct challenge to the way our senses and instincts carve out meaning from the world. In the cosmos, there is no preferred frame, no cosmic home base, only the dizzying sameness of infinity. Night after night, the sky stays dark. For centuries, that simple fact puzzled astronomers. If the universe were infinite and filled with stars, every line of sight should end on a blazing sun. The darkness overhead, Olber's paradox, suggests something is deeply wrong with our expectations. The answer comes not from the stars themselves, but from the boundaries set by time and space. The universe has a finite age, about 13.8 billion years. Light from the most distant stars has not had enough time to reach us. Expansion stretches the space between galaxies, shifting ancient starlight into invisible wavelengths. The result is a sky far dimmer than our minds predict. In 1965, 2 engineers at Bell Labs, Arno Penzias and Robert Wilson, stumbled on a faint hiss of microwave noise coming from every direction. They tried cleaning their antenna, even removing pigeon droppings, but the noise never faded. What they had found was the afterglow of the Big Bang, the cosmic microwave background, or CMB. This radiation, now cooled to just 2.7 degrees above absolute zero, fills the universe with a near-perfect uniformity, its temperature varying by only about 1 part in 100,000. Those tiny ripples seeded all future galaxies, yet the overall smoothness is almost absolute. The CMB sets a hard horizon. We cannot see beyond it, because the universe before that moment was opaque. Some boundaries are even more permanent. In the first 10 to the minus 32 seconds, the universe underwent inflation, ballooning faster than light and separating regions forever. No signal, no telescope, no theory can ever reach past those cosmic horizons. The universe draws a line that even imagination cannot cross. For minds shaped to seek answers everywhere, these limits are not just physical, they are existential. The sky's darkness, the hiss of ancient microwaves, and the unreachable edges all reveal a cosmos with horizons built into its very fabric. Time, as experienced in daily life, feels absolute, a steady, universal flow that everyone shares. But the universe refuses to cooperate with this intuition. In 1971, physicists Joseph Haffel and Richard Keating carried 4 atomic clocks onto commercial jets, flying twice around the world in opposite directions. When the clocks returned, they no longer agreed. The eastward clocks lagged behind by about 59 nanoseconds, while the westward clocks gained 273 nanoseconds, matching Einstein's predictions for time dilation. Even a journey on an airplane pulls travelers out of sync with those on the ground, if only by billionths of a second. The effect grows with speed and gravity. Astronauts aboard the International Space Station circle Earth at 28,000 kilometers per hour. Over 6 months, their clocks fall behind those on the ground by about 0.007 seconds, a measurable difference that engineers must correct for. The global positioning system relies on constant adjustments. Each GPS satellite carries atomic clocks that tick faster in orbit than on Earth's surface, thanks to weaker gravity, but also run slower due to their speed. Without daily corrections for these relativistic quirks, GPS locations would drift by kilometers in a single day. Physicist Sean Carroll explains that this isn't a technical glitch, it's a clue to how reality works. There is no single now that stretches across the cosmos. Every observer, moving at their own speed or sitting in their own gravitational well, slices time differently. The present is not a universal stage, but a local perspective shaped by motion and mass. What feels like a shared moment is, in truth, a patchwork of personal timelines stitched together by the laws of relativity. Equations in physics don't care which way time runs. The math that describes a bouncing ball or an orbiting planet works just as well forwards as backwards. But daily life tells a different story. A glass shatters, but never leaps whole from a pile of shards. Milk mixes into coffee, but never unmixes itself. This one-way flow is the arrow of time, and it comes not from the deepest laws, but from the march of entropy, the tendency for disorder to increase. The second law of thermodynamics states that in a closed system, chaos always grows. It's this statistical drift toward messiness that gives time its direction, not any fundamental rule. Yet even this arrow is fragile. In the world of atoms and molecules, every collision could just as easily run in reverse. The only reason we see eggs break and not reassemble is because there are vastly more ways for things to be messy than to be neat. The universe began in a state of low entropy, and ever since, the odds have favored disorder. This is a matter of probability, not destiny. Chaos theory adds another twist. In the 1960s, meteorologist Edward Lorenz discovered that tiny differences in starting conditions can make weather forecasts diverge wildly, a phenomenon he called the butterfly effect. Even with perfect equations, the outcome can be unpredictable. Small uncertainties snowball, making long-term prediction impossible. The future isn't written in the laws of physics alone. It's shaped by a relentless drift toward disorder and the sensitive dependence on initial conditions. The arrow of time, so obvious in daily life, is built on a foundation of chance and chaos, not inevitability. Equations at the frontiers of physics allow possibilities that stretch the mind to its breaking point. Einstein's general relativity predicts that spacetime can, in theory, be twisted into loops, closed, time-like curves, where the future connects back to its own past. In 1988, physicists Kip Thorne and Michael Morris published solutions describing traversable wormholes, mathematical tunnels that could link distant points in space and time. These aren't just science fiction props. The equations themselves permit shortcuts that, if stabilized, could let a traveler double back and meet their younger self. But such scenarios are haunted by paradoxes. What happens if someone prevents their own birth? The laws that seem so solid on human scales dissolve into uncertainty when time itself is allowed to circle back. At the other extreme, the beginning of the universe stands as a wall to all intuition. The Big Bang wasn't an explosion in space, it was the birth of space and time themselves. Asking what came before is like asking what's north of the North Pole. The Planck epoch, the first 10 to the minus 43 seconds, remains a singularity where the known laws of physics collapse. No experiment, no observation, not even the most advanced mathematics can peer past this boundary. Causality, our deepest anchor in understanding, fails at the very moment it is needed most. The universe offers no starting gun, no before, only a horizon beyond which questions themselves unravel. For a brain that craves sequence and explanation, this is the ultimate disquiet, a cosmos where the chain of cause and effect has a missing link, and the story of everything begins with a page already torn away. A Geiger counter waits beside a lump of uranium. Hours pass in silence, then click. Another long pause, then a burst of static. The pattern never settles. No force or law can predict the exact moment an atom will spit out a particle. Each decay is a roll of the cosmic dice, obeying only the cold statistics of probability. If you count 1,000 decays, the numbers will match the Poisson curve perfectly. But which atom goes next and when? Not even the universe knows. This is quantum indeterminacy, outcomes governed not by hidden gears, but by chance itself. The strangeness deepens with the double-slit experiment. Fire electrons, one at a time, at a barrier with two narrow slits. Each electron lands as a single dot on a screen, like a tiny bullet. But after thousands of shots, a ghostly pattern of stripes appears, an interference pattern, as if each electron were a wave passing through both slits at once, then interfering with itself. Block one slit and the stripes vanish. Open both and the pattern returns. Electrons refuse a single identity, sometimes wave, sometimes particle, never both at once unless watched. As physicist Anton Zeilinger put it, the border between reality and our knowledge of reality is not absolute. The mind aches for certainty, for objects that are either here or there, for causes that guarantee effects. But at the quantum scale, identity blurs and randomness rules. The universe's smallest pieces do not behave, they misbehave, defying every rule that feels natural to the human brain. At the quantum scale, certainty is traded away piece by piece. The more precisely you pin down an electron's position, the less you can know about its momentum. Heisenberg's uncertainty principle, written as delta x times delta p, is always greater than or equal to a tiny constant. This is not a flaw in measurement or a gap in technology. It is a hard boundary set by nature itself. Try to trap an electron in a narrow space, and its possible speeds explode into a blur. Let its momentum settle, and its location becomes a fog. Every act of observation slices away one kind of knowledge to gain another. The boundary between what is and what is measured grows even stranger. In delayed choice experiments, a particle's behavior, wave or particle, can be decided even after it has entered the apparatus. The universe seems to wait for a question before deciding on an answer, as if reality and measurement are entangled in a dance with no clear lead. Schrödinger's cat, both alive and dead until the box is opened, is not just a thought experiment, but a symptom of a deeper problem. There is no sharp line between observer and observed. The mind wants the world to exist independently, with facts settled before anyone looks. But the quantum world refuses to play along. Knowledge itself is carved out of possibility only by the act of questioning. The deeper you look, the more the edges of reality dissolve into uncertainty, leaving a universe that is not just unknown, but fundamentally unknowable in its details. Two photons are created together, then sent in opposite directions, separated by more than a kilometer of air and concrete. Each one travels alone, with nothing to connect them except a shared past. When physicists measure the polarization of one photon, the result instantly determines the outcome for its distant partner, even when the two are too far apart for any signal, even light, to pass between them in time. This is quantum entanglement, the phenomenon that so unsettled Einstein, he called it spooky action at a distance. For decades, skeptics wondered if hidden variables or experimental flaws might explain away these instant correlations. But in 2015, a series of experiments slammed shut the last loopholes. At Delft University in the Netherlands, researchers entangled electrons in diamond chips, then measured their states 1.3 kilometers apart. The results matched quantum predictions, violating Bell's inequalities and ruling out any local classical explanation. Similar tests with photons at distances up to 1.3 kilometers confirmed the effect. The outcomes on each side correlated more strongly than any theory of local realism could allow, even when measurements were chosen at random and detectors were shielded from outside interference. Entanglement does not allow messages to travel faster than light. No information leaps between the particles. Instead, the universe simply refuses to be local or solid in the way the brain expects. What happens to one particle is instantly reflected in the other, no matter the distance. The rules of cause and effect, so deeply wired into human intuition, break down at the quantum level. Reality is stitched together by invisible threads that defy every instinct about space, distance, and separation. Empty space is anything but empty. In 1948, Dutch physicist Hendrik Casimir set up a simple experiment. Two metal plates, placed a hair's breadth apart in a vacuum. No particles, no air, just nothing between them. Yet the plates nudged together, drawn by a force out of nowhere. This Casimir effect, measured at about 1/10,000,000th of a Newton, proved that even the purest vacuum seethes with activity. Quantum fields flicker, spawning pairs of particles and antiparticles that blink in and out of existence, leaving behind a pressure you can actually measure. Nothingness, it turns out, is a restless stage, not a blank slate. Across the universe, something even stranger passes through us every second. Trillions of neutrinos, ghostly particles with almost no mass, stream from the sun, from distant supernovae, and from the radioactive decay of elements in Earth's core. Each second, about 65 billion neutrinos zip through every square centimeter of your skin, day and night. They almost never interact, slipping through the entire planet as if it were smoke. Only massive detectors like the Ice Cube Observatory, buried under 1 kilometer of Antarctic ice, can spot the rare flashes when a neutrino finally collides with an atom. To human senses, these particles and the vacuum's invisible flicker are utterly silent. But the numbers reveal a universe alive with hidden motion, activity so constant and so subtle that it escapes every instinct about what it means for something to be truly empty. Galaxies spin with a speed that refuses to slow down, even at their edges. Vera Rubin spent years measuring the rotation curves of spiral galaxies, expecting the stars on the outskirts to lag behind, just as planets far from the sun move more slowly. Instead, she found the speeds stayed flat, evidence that most of the mass was invisible, hidden in a halo around each galaxy. Rubin's late-night observations at Palomar Observatory, often in the face of skepticism and isolation, forced astronomers to confront the reality of dark matter. Today, estimates suggest that 85% of the universe's matter is dark, undetectable except through its gravitational pull. Ordinary atoms, the kind that make up stars, planets and people, account for just a sliver. The puzzle deepens with dark energy. In 1998, two rival teams, led by Saul Perlmutter and Adam Rees, tracked distant supernovae to measure how fast the universe was expanding. Both groups expected to see the expansion slowing under gravity's pull. Instead, their data revealed acceleration, a discovery so unexpected it won the Nobel Prize in 2011. Dark energy, making up about 68% of the universe's total energy, acts as a kind of anti-gravity, pushing galaxies apart faster over time. The cosmos is dominated by forces and substances that cannot be seen or touched, only inferred from the way they shape what little we can observe. As Rubin once said, "We are made of the leftovers." Change the strong nuclear force by just 1% and the universe erases its own chemistry. A slight increase, and stars burn too quickly, fusing hydrogen into helium before heavier elements can form. Decrease it, and atomic nuclei fall apart. The cosmos fills with nothing but hydrogen, no carbon, no oxygen, no life. The tolerance is razor thin. Less than a 2% wiggle room separates a universe that builds complexity from one that collapses into simplicity. The same precision appears in the balance of gravity and electromagnetism, the masses of quarks, and the energy of the vacuum itself. The cosmological constant responsible for the universe's accelerated expansion differs from quantum field theory predictions by a factor of 10 to the 120th power. No other number in science misses the mark so spectacularly. These numbers are not the product of visual design, but of mathematics written deep in the universe's structure. Some physicists argue that if there are countless universes, each with different constants, then ours is simply one where the math happens to work. Others point to the anthropic principle. We find ourselves here because only this kind of universe allows observers to exist at all. The logic loops back on itself, offering an answer that feels more like a mirror than a map. The mind searches for meaning in the decimals, but the equations remain silent. At the edge of knowledge, the universe offers only numbers, unreasonably effective, impossibly fine-tuned, and utterly indifferent to the need for explanation. Right now, our most advanced theories still collide with the limits of human intuition. As we map only 0.0035% of the electromagnetic spectrum and encounter constants science can't reconcile, we face the humbling truth. Reality resists fitting into our cognitive comfort zones. Progress demands we question, not conform. The universe doesn't owe us sense, yet our curiosity refuses to yield. Sometimes, the only way forward is to embrace the strangeness. Share your perspective below.